Today we're going to look at section 7.3. This section is going to have us use formulas involving sides, angles, and diagonals of polygons. So we need to know the vocab dealing with polygons. We know that a polygon has to have segments forming them, so no curves, and all of the segments have to be connected. So the smallest polygon is a three-sided polygon, which we should be very familiar with. Those are triangles. We've also talked about four-sided polygons in our last chapter. The most basic four-sided figure would be called a quadrilateral. So then some of these names hopefully look familiar to you, but anytime we're talking about 5 sides, it is a pentagon. 6 sides is a hexagon. 7 sides is a heptagon. 8 sides is an octagon. 9 sides is a nonagon. 10 sides is a decagon. We skip 11, I'll come back to that in a second. 12 sides would be a dodecagon. We'll skip a few sides. 15 is a pentadecagon. And then we have n, which is an n-gon. So essentially, these numbers, 3 through 10, 12, and 15, those are the number of sides where you absolutely have to know the vocab. But like I said, like 11 sides was skipped, and 13 and 14, and anything bigger than 15. So that's where this n comes in. So say I wanted to know what an 11-sided polygon was. Well, if there are 11 sides, then what I would say is that it is an 11-gon. So the n is just representing another number other than the numbers that I have listed here. We would literally then just put that number and then put the word gon after it. All right, so let's use that vocab to do some problems after we look at the formulas that are going to be important here. So here are the 3 formulas that we have to know when we are dealing with sides, angles, and diagonals of polygons. So it says the sum, S sub I, of the measures of the angles of a polygon with n sides is given by the formula. Now it's S sub I, so that little I is just telling us that these are angles that are inside of the polygon. Okay, so n represents the number of sides, but hopefully we recognize that the number of sides is also the number of angles of that polygon. Because think about a triangle. You have 3 sides of a triangle. You also have 3 angles of a triangle. Think about a quadrilateral, 4 sides, 4 angles. So there's always that relationship. So once again, that n is representing either the number of sides or angles. So if I want to figure out what all of the angles add up to, it's n minus 2 being multiplied by 180. So that is a formula that we're going to have to get very familiar with. In the middle, it says if one exterior angle is taken at each vertex, the sum, S sub E, so once again that E stands for exterior, so the sum of all the angles outside of the polygon is going to always be equal to 360 degrees. So it's not per se a formula, as more is just a number. So every single exterior angle, so let me sketch a picture here for you. So say I have a triangle. So obviously all the angles inside are interior. So if I extend this side, there's an exterior angle. If I extend this side, exterior angle. If I extend that side, exterior angle. So those 3 angles would always add up to 360. And it doesn't just have to be a triangle. It could be a 100-sided shape. Its exterior angles will always add to 360. And then the last formula, it says the number d of diagonals that can be drawn in a polygon of n sides is given by the formula. So we always can define our diagonals by taking n times n minus 3 and dividing that whole thing by 2. So once again, n represents the number of sides, which is also the number of angles. So whatever that is, we can plug that number into both of those n's, and we can use this formula to tell us how many diagonals are in the polygon. So let's use these 3 formulas to answer some of these questions, and let's also use the vocab. So it says find the sum of the measures of the angles of a dodecagon, and a 93 gon. So in the directions, anytime it's talking about the sum of the measures of the angles, it's not going to necessarily say interior or exterior, but I hope you understand that if it's the sum of the measures of the angles, we are talking about interior angles here. So in this direction, we are talking about interior angles. In part A, if it's saying a dodecagon, well, that's going to tell us exactly what n is. N is going to be, in this case, 12, based off that list of all the vocab that we just talked about. So remember, if we're talking about the sum of our interior angles, I want n minus 2 times 180. So I know what n is, so I'm going to take 12 minus 2, multiply it by 180, and that's going to tell me what all the angles add up to. Okay, so the sum of all of those angles then would be 10 times 180, so it looks like 1,800 degrees is going to be what all of those angles, all those 12 angles are going to have to add up to. Okay, notice that in this case, they're saying a 93 gon. So that means that n equals 93. So there are 93 sides, which means there are 93 angles. So once again, we're using the sum of the interior angles, so n minus 2 times 180. I'm going to substitute in 93 for n. So 93 minus 2 is going to give me 91. That has to get multiplied by 180. So 91 times 180 tells us that we have 16,380 degrees. So that's what all 93 angles would add up to in this particular polygon. Okay, so it says find the missing angle measures. Notice that. Let's count up the number of angles that we have. So if I start here at angle with A, so we've got 1, and if I'm going to go clockwise, so 1, 2, 3, 4, 5, 6, 7. So that looks like there are 7 angles. So remember, if there's 7 angles, that means that there are 7 sides. And so vocab-wise, this is a heptagon. All right, so we're dealing with a heptagon. We're finding the measure of the missing angles. We'll notice that there are 2 of them, but they are marked the same. So they are congruent. So instead of saying A and B, let's call it X and X. But I know that all 7 of those angles, let's figure out what it has to equal. Okay, remember 7 minus 2 times 180 is going to tell me what all 7 of those angles have to add up to. Well, 7 minus 2 is 5, so really 5 times 180 is going to tell me. So that tells me that all 7 of those angles have to add up to 900 degrees. So once I understand that information, now that I have the measures of all of those angles besides what I call X, well, let's add them up and set it equal to 900. So I'm going to start at A again, and I'm going to go clockwise. So we've got X plus 120 plus 150 plus X plus 140 plus 120 plus 160. So there's all 7 of them, and we just found out that they have to add up to 900. So we've got X's to combine, so that gives me 2X, and now I'm going to add up all those numbers. So 120 plus 150 plus 140 plus 120 plus 160, that looks like that's going to give us 690 degrees. So let's start solving for X. I'm going to subtract 690 from 900. And so that's going to give us 210. I'll divide both sides by 2. And then remember, X is both angle A as well as angle B. So it looks like each of those are 105 degrees. Okay, but I had to know what all of those angles added up to, so we had to use that formula n minus 2 times 180 to make that happen first. All right, this time it says find the number of diagonals. So remember, the formula for diagonals is n times n minus 3 all divided by 2. So that's the formula that we're going to use. In part A, it says we have a pentadecagon. So we can identify what that is for the value of n. A pentadecagon is 15 sides. So I'm going to use that, substitute that into the two different spots in the formula so I can figure out how many diagonals we have. So we're going to have 15 times 15 minus 3, but that whole thing is being divided by 2. So really we'll have 15 times 12 being divided by 2. Well, 15 times 12 is going to give us 180. And 180 divided by 2 tells us that there are 90 diagonals. Okay, diagonals are segments, so I don't put a degree symbol with it. And hopefully that makes sense that I would definitely not want to try to add or to draw that and add them up, because it would take us quite a while if we're dealing with 90 diagonals. And that's just with 15 sides. So can you imagine here in part B, if it says 72 gone, that means that n is 72. So we have 72 sides. Let's figure out how many diagonals we have. So I'm going to plug that into the two different n's in my formula. So 72 times 72 minus 3, and that whole thing is getting divided by 2. Well, 72 divided by 3 is 69. Let's see, 72 times 69 looks like that's going to give us 4,968. Divide that by 2, and it looks like the number of diagonals we have is 2,484. So quite a few diagonals there. But we had to know what we were substituting in for n. We had to know what our formula was. So that's us using formulas involving sides, angles, and diagonals of polygons.